Hello, it's a great pleasure to be back in Berkeley area.
You've written a very engaging and insightful book, The Road to Reality, A Complete Guide to the Laws of the Universe. Could you tell us a little bit about it and what motivated you in writing it?
Yes, well, the book is meant to describe what's going on in basic physics today and what led up to that in terms which are a bit more technical than the accounts that you normally get in popular books. So it was an attempt to describe things at a deeper level than you can usually get access to without going to the full thing and reading a textbook. I should perhaps explain the origin of the book, which might be of some interest to people. Some years ago I wrote a book called The Emperor's New Mind, and that book was describing a point of view which I had about consciousness and why it was not something that comes about from complicated calculations. So we're not exactly computers, something else going on, and the question of what the something else was would depend on some detailed physics, was the idea. And so I needed to have chapters in that book which describes the physics as it's understood today. Well, anyway, this book was written, and various people commented to me. They said, well, I could perhaps use this book for a course, Physics for Poets, or whatever it is, if it didn't have all that contentious stuff about the mind in it. So I thought, well, that doesn't sound too hard. All I do is I get my scissors out and snip out all the bits which have something to do with the mind. The trouble is that if I did that, and I didn't actually do it, but I sort of imagined doing it, the whole book fell to pieces, really, because the whole driving force behind the book was this quest to find out, what could it be that constitutes consciousness in the physical world as we know it, or as we might hope to know it in the future. But without that driving force, the book sort of didn't hang together, really. So I had to think of some other basis for this. See, initially I thought of a book about half as long as the other, and the other one's about 400 hours. The search for the laws which govern the universe at its deepest level, that kind of thing. So that meant I had to include a lot of other things in the book, and a lot of mathematics, because I wanted to explain it at the same sort of detail as I did in The Emperor's New Mind, or maybe a bit more. And this required describing a lot of mathematical ideas in some, not too much detail, but to give the gist, the basic feeling for what was really going on. And I made a list of all the different mathematical topics, and I was rather horrified to see how many there were. And it was even worse in a sense, because when I wrote the book, I kept realizing there were topics I hadn't really covered and needed to put them in somewhere. So it made for a long book, I'm afraid. But you have the advantage with the US printing, I should say, because the paper is just slightly thinner, so the whole book is not quite so big, and it doesn't weigh quite so much, and the paper is better quality, so the pictures and the printing looks better too.
Great. So let's talk a little bit about physics. In string theory, the particles in the universe are generated by the vibration of loops of constructs known as strings. The mathematical framework for describing these loops require multiple dimensions, and one variation requires up to 26, while the conventional model relies on 10. In your twistor theory, you can do away with all these extra dimensions. Can you explain that a little bit, perhaps?
Yes. Let me just backtrack a little bit. That, as you say, the way string theory works seems to require all these extra dimensions, and this comes from certain consistency requirements about how strings should behave and so on. Now, twistor theory is something quite different. It's an approach to understanding how space-time and quantum mechanics might fit together in some way. But the basic idea in twistor theory is not to add extra dimensions. In fact, it's very crucially only 3 space dimensions and 1 time dimension. It's the number of dimensions we experience. But instead of adding extra dimensions, it's a reformulation of the space-time as we understand it. So instead of thinking of points as being the fundamental entities, which is what you usually do when you think of space-time or events, points, instantaneous points, you think of entire light rays. It's not quite that. Entire light rays, you see, if you made a space, each of whose points represented an entire light ray, you'd find that space had 5 dimensions. Now, one of the basic driving forces behind twistor theory is to find a theory which is based fundamentally on complex numbers. Now, you see, complex numbers, where you involve the square root of -1 into ordinary real numbers, they've been very useful in mathematics for many, many centuries. Only in the 20th century did they start to find a fundamental role to play in physics, namely in quantum mechanics. So suddenly you find these wonderful numbers that worked so well in mathematics but didn't seem to have any role to play in the physical world, suddenly they did have a role to play in the physical world. Well, twistor theory is trying to take that one step further. So you look for a role for these complex numbers, complex spaces, and so on, to have a role in space-time geometry. And what you find is that if you look at light rays instead of points, you find almost, and I'll qualify this almost in a minute, or explain it in a minute, you find almost that the space of light rays is a complex space. It can't quite be, because the space of light rays is 5-dimensional, and any complex space has to be an even number of dimensions, because each dimension counts as 2 dimensions. See, the real and the imaginary parts. So where is the extra dimension? Well, what you find is that if you don't just think of light rays as sort of a path of a single point, but you think of it as something spread out which has a spin. So it's in actual fact, ordinary photons do have a spin. They have a notion of helicity, so they spin around their direction of motion, and they can spin one way or the other way, and they can also have a different energy. And what you find is if you incorporate these ideas into your photon, that you get another dimension, and you therefore get 6 dimensions, and miraculously this 6-dimensional space is a complex space. So the idea of twistor theory is to take that complex space and you try to work with that. Now you see it's completely equivalent to the space-time description. You can use one or you can use the other, so you say why does it matter? But you're sort of driven in different directions. If you take twistor space as the basic geometry, then you find it's naturally complex, and you do things which are naturally complex, and it drives you in a certain direction. And that's basically what twistor theory is about. Basically, it's a reformulation of geometry in a way which is more compatible with quantum mechanics. As it stands, it doesn't change any physics. It's just a different way of representing it. But I should say that there's a bit of an irony in this, that in the book I make the point that here we've got string theory and here we've got twistor theory, and we don't know if either of them is a right approach to nature. But they can't both be, because they are incompatible in the sense of having different number of space dimensions. Well, the irony is that just a bit over a year ago, Edward Witten, who's the sort of one of the prime, he is the sort of prime mover in modern string theory. Yes, at Princeton, that's right. And he's introduced many very ingenious notions which have pushed string theory forward in many ways. And he wrote a paper which appeared on the web in December in 2003, in which he combines the ideas of string theory and twistor theory. So the idea is basically you don't put your strings in these extra dimensions. That's what people have been doing up to this point. You put them in twistor space. And twistor space is already there, you see. It doesn't need any more spatial dimensions. In fact, you shouldn't have any more spatial dimensions. It's already there. And you can put the strings in that space. And then what he also finds is that this enables you to much more easily obtain sort of formulae which describe gluon scattering. So this is to do with high-energy physics, strong interactions, and things which are actually measured in accelerators. So this is actually giving you results, this is quite new in string theory, if you like, results which are physically measurable, physically observable. So I find this development a very exciting one, and fortunately in the book I did manage to catch this before, so I do mention these ideas, not in any detail because it was only just at the last minute.
I'm just curious here, could you also explain the essence of gauge theory?
Well, gauge theories, of course, gauge theories are very fundamental to our understanding of physical forces these days, but they also depend on a mathematical idea which has been around for longer than gauge theory has. Well, actually, I'm not sure about that, because Hermann Weyl, who introduced the idea of gauge theory, maybe that came before the ideas of bundles. But the idea of a fiber bundle and the connection on a fiber bundle is basically what gauge theories use. And so I do describe this in the book. There's a chapter on these things. Still in the mathematical part, so that you're just doing mathematics at that stage. But let me describe Weyl's original idea, because I think that gives you, it's the best way of phrasing it so that you can understand what's going on. You see, Einstein introduced general relativity or even before that, think of special relativity, and there's a thing called the clock paradox or the twin paradox. It's not really a paradox, but it's if you have these two people, one who stays still on the Earth and the other one goes in a rocket ship to a distant star and comes back again, and you find that the one who's gone off and comes back has experienced less time than the one back on the Earth. But what you don't find is that their clocks run at a different rate. You see, the one who's gone off and come back again, he brings his clock and it's slow, you see. Time hasn't moved forward by as much, but it still ticks at the same rate as your clock does. But in Weil's theory, which he introduced as a generalization of Einstein's theory, the idea was that you could incorporate electromagnetism as well as gravity. And Weil's idea was to say, well, why not generalize general relativity? So instead of having clocks with the clock paradox, which, it can be slow, but it's not running slow, let's suppose it might run slow. So that in fact, if you go different routes through space you come back to the same point, you compare clocks and you find one of them is actually running at a different rate from the other one. And if you introduce that idea, you can get a formalism which incorporates equations just like Maxwell's equations. And Weil's idea was this is a unified field theory which includes electromagnetism. Well, there's a minus and a plus to this. The minus was really Einstein pointed out that this can't be right. And we know that this would mean particles would have different masses depending on what routes they take, and it's really incompatible with the facts. So that was a bit of a disappointment to Weil. But the upside of all this was that a little while later, when the ideas of quantum mechanics came in, Weil and other people changed their view as to what this theory was, that it wasn't a change in clock rates, if you like, or in the scale of the metric, which comes to the same thing, but it was a change in the phase of the quantum mechanical phase. So you have not a real number, which would be a stretching, the time rate could be stretched or squashed. That would be a real parameter, but it's a complex parameter, which is a phase. So you're going around the unit circle. You're multiplying by e to the I theta or something like this. And with this idea, you could incorporate electromagnetism in a way which was consistent. And in fact, that's the way it's done now. This idea of Weil's that's the first gauge theory. It was a way of representing Maxwell equations and how the electric fields, electromagnetic fields interact with particles in quantum mechanics. And it's exactly the way we do it. Now, that's the first gauge theory. It's called a gauge theory because the original Weil idea was a gauge. You see, it was a change of scale. But then it became a complex change, and it's not so appropriate really to call it a gauge, but it's the same idea. But then this idea was generalized by Pauli and then by, I think, Shaw, and then Yang and Mills independently a little bit later, but they were the ones who really developed the theory and people picked up on it. So this is an idea called Yang-Mills theory, and it's found that this idea, in a somewhat more general form than Weil had, which was just this phase, but you have a group which is bigger than that. It's the basis of forces according to modern particle physics. Both the weak interactions and the strong interactions are supposed to take place according to such a theory.
In quantum theory, we are confronted with the paradox of Schrödinger's cat, where the cat is characterized as being a superposition of dead or alive until it is observed. Now, I understand you've collaborated with Stephen Hawking, and he's known for saying, every time I hear about Schrödinger's cat, I reach for my gun. What does he mean there? Do you agree with him?
But it's a pity he has to quote Hermann Goering on this. I believe the quote was not original with Hermann Goering. It goes back before that. It's I don't much like that criticism. It's not really a criticism. It's just a feeling he doesn't like the idea. But it doesn't get you around the problem. I mean, Schrödinger pointed this problem out very clearly, and I think absolutely Schrödinger was absolutely right. He was saying, look, if you apply my equation, that's Schrödinger's equation, to something of the scale of a cat, you get this nonsense, which is a dead and alive cat at the same time. So he's more or less saying that. And he was saying, look, you shouldn't be using my equation, Schrödinger's equation, to describe a thing like a cat. Something else basically has to come in. Now, he didn't make any suggestion as to what that might mean, but I think he's right. And although all sorts of points of view are developed to try and accommodate Schrödinger's cat one way or the other, well, the main two are that somehow environmental decoherence, it's called. Somehow the state gets so complicated and mixed up with the environment that you have to change your procedures. None of these things really work if you follow them through. The second one is what's called many worlds interpretation. You say, okay, the cat is there in these two superposed states, and if somebody comes along and looks at it, then that person now has two superposed versions of them, one seeing the live cat, one seeing the dead cat, and they're in superposition too. And then the argument is somehow that there's a bit of you have to be a bit generous about the point of view here, that somehow your conscious perceptions must perceive either the live cat or the dead cat. And it's not really explained why, because according to Schrödinger's equation, you ought to be perceiving them both at the same time. And that's not what we actually perceive. So it's where you're driven if you don't believe there should be a change in quantum mechanics. You're driven to this many worlds view. But it doesn't get you out of the problem. You're driven there, but you still have the problem. So what I'm saying is, why don't we think about changing Schrödinger's equation at some level when masses become too big, in a sense, and at the level where you might have to worry about Einstein's general relativity. So that's my own view, and that there will be a change in the structure of quantum mechanics at that level. Another way of saying this is it's a question of what's quantum gravity. You see, most people think quantum gravity means you apply standard quantum theory to the structure of space-time, and this means you'll have to do something different about space-time structure. Okay, I don't have any qualms or quarrels with that, but what I worry about is why standard quantum mechanics. Now, of course, I can see why people, when they do quantum gravity, why they don't change quantum mechanics, because if you change that, you're pretty well, you've changed everything, so what do, you see? So I can see that it doesn't tell you where to go. Nevertheless, it might be what nature is doing. And I think there are good reasons to believe that that is what nature is doing, that there are changes in the structure of quantum mechanics at that level. And there are several different independent reasons for believing this that are described in this book. So a lot of the book, a major part of the book, I would say, is devoted to this issue in different aspects, so it's spread over several chapters.
So Steve Wolfram's famously known for developing Mathematica, and he's also a pioneer of cellular automata, which lets you create complex patterns from simple algorithms. Do you see any promise or insight using these methodologies?
Well, I think these are interesting ideas, and he certainly develops them to quite a considerable degree. But I don't myself believe there's any evidence that these ideas are playing a big role in physics. So certainly none of the standard physical theories can be thought of as cellular automata in any clear sense.
Looking back, what's your most cherished epiphany?
You mean what the thing that I'm most proud of? Well, I think it has to be twistor theory. I mean, it may not be the thing that most people know about that I've done. I mean, maybe the non-periodic tilings or something. But no, but twistor theory is the thing that I would like to be remembered for most, I suppose, if that's...
So what are your thoughts about Kant and Hegel? Hegel describes a very different road to reality, history as a dialectical series of events. You end the preface in your new book with a wonderfully wise statement about the need to study the forces that really shape the world. Can you share us your thoughts about the human experience beyond physics?
Well, I don't know that I can comment on Kant or Hegel, because I'm no real philosopher in the sense of knowing what these people have said in any detail, so let me not comment on that too much. But I suppose I do think that, you see, this book is about physics, and it's about physics and its relationship with mathematics. So it's about physics and mathematics, and how they seem to be intimately related, and to what extent can you explore this relationship and trust it. Just at the end of the book, I do mention what you can regard as the sort of other Platonic absolutes. So if you like, what I've been concerned with is the Platonic absolute of truth in its particular form, that is mathematical truth, which is a sort of very idealized form of truth. But I think it's a serious issue to wonder about the other Platonic absolutes of say, beauty and morality. I don't think the case for them is as clear as it is for truth, but on the other hand, there does seem to be some connection between beauty and the search for these laws that govern the world, and that you certainly find that people are driven with this beauty as a sort of criterion or a guide to discovery in this context. And as for morality, well, that's all tied up with the question of consciousness. If you didn't have any conscious beings in the world, there wouldn't really be any morality, but with consciousness, that you have that. So I think that the issue of how consciousness relates to the physical world is all tied up with morality, but we have a lot to learn on that one.
Finally, on a lighter note, let's talk about pop culture. Reality and existence are recurring themes in movies and books. Questions including who are we, what is real. Are you amused by how these are treated in, say, for example, movies like The Matrix?
Well, I didn't actually see The Matrix, but I've seen other movies where maybe similar sorts of themes. I mean, I find it amusing and entertaining, and I've always been a fan of science fiction. I used to read it a lot when I was younger, and I like science fiction movies. But I think they're useful for giving us ideas, and I think that's true. I think science fiction is very good at giving ideas. But on the other hand, you have to take it all with a suitable amount of salt. And I certainly don't believe that these things like, Terminator or something coming from the future, who's a mechanical entity, but I think they raise issues often too, which are not trivial issues. So yeah, I enjoy them.
Professor Penrose, thanks for joining us on Berkeley Rocks. Thanks for your time.
It's a great pleasure. Thank you very much too.